Hello, everyone, and welcome to another live edition of the Learn It, Turn It, Burn It Torque and Drag mini series. This is episode number 6, I think. Yeah, we're at episode number 6 now, brought to you by WWT, an absolutely amazing sponsor. And yes, we will be giving away a drill bit. All right, guys, let me know where you're watching from. Let me know how many of the mini series episodes so far that you have watched. If there are any in particular that you are truly fond of or that you learned a lot from. We've also been posting onto LinkedIn all of the PowerPoint presentations from each one of the episodes prior. So be sure and go and check those out so that you can continue on with your educational learning and stuff. All of those are on the main page of my LinkedIn profile. Speaking of LinkedIn profile, right? If you want to be able to get notifications of when we're going live for this and or the Vidor Locksmith show right here, you can just click the notification icon if you're over on my page, or click the follow button to be able to get updated on any of the stuff that's going on. And I have to say, special happy Valentine's Day to everybody out there. Today's Valentine's Day is very special to me, so my special someone got me a PDC shaped drill bit box with little chocolate drill bits inside of it. Oh, very, very sweet. So just want to be able to show that. It was very, very sweet gesture to be able to receive this morning. All right, guys, thank you guys all so much for being here. Do appreciate it. Like I said, today's episode is brought to you by WWT, and we've already got tons of people tuning in. Much thanks. He's already saying hashtag WWT. Randy's on the ball here. He knows how this thing works. He already knows what I'm going to say. So he's getting his vote in there already. Francis tuning in from the Woodlands. Thanks for being here. Brad Watson becoming a show regular. Thanks for being here. Remy tuning in from France. Mark from Dubai. Muhammad from Austin. Thanks for being here. Mr. Ediberto from Colombia. John DeWart tuning in from Colorado. Thank you for being here, sir. Clifford J, one of the K&M team out there in from WND West Texas. Windy West Texas. I was like, oh, okay. Yeah, I can't read. Sorry, guys. Another part of the K&M team, Rodney White. Thanks for being here. Vizad tuning in from Calgary. Robert Carrington, the Vibration Technology team. Thanks for tuning in. Lieb tuning in from Houston, Texas. We've got Cypress, Texas tuning in. Mauricio from Katy, Texas. Roberto from Austin, Texas. Debbie tuning in. Love chocolate drill bits. Washington from Houston, Texas. Thanks for being here. Eric says, Mael. I'm not really sure about that one. Deborah from Ontario, Canada. See, Adrian's getting on the ball too here, already putting in the hashtag WWT. Carlos from Colombia, Alfredo from Woodlands, Texas, and Ari from watching in Dubai. Yes, yeah, guys, if definitely that is the trick of the day. If you want to be able to win yourself a giant drill bit, hashtag WWT, and we will be sending out one of these. Maybe, just maybe, if whoever wins is from the U.S., because I don't know if I can send Chocolate International, and even if it would make it, but maybe if whoever wins is from like the Houston area or something like that, I'll give you one of the chocolate drill bits as well. So put in hashtag WWT right now, and we'd love to be able to hear here's our word from our sponsor of today's episode. So check this out.
WWT non-rotating protectors, otherwise referred to as NRPs, are the world's most widely used mechanical drill string, torque, and friction reduction tools. NRPs optimize drilling performance by delivering maximum energy to the bit while reducing torque, drag, casing and riser wear, heat checking, and buckling. Friction occurs when the drill string rotates and slides in the wellbore. WWT's patented fluid-bearing technology within the NRP sleeve creates maximum torque reduction. WWT provides a torque and drag analysis to identify specific areas within the wellbore to place NRPs. NRPs are typically placed across intervals where high side forces are analyzed, such as build or drop sections of the wellbore. NRPs are commonly used in horizontal, S-shaped, extended reach, and even vertical wells when unexpected dog legs are encountered. Unlike conventional rotating drill pipe protectors, the patented NRP rotates minimally to provide torque reduction without adversely affecting axial drag. NRPs provide the most efficient solution for reducing friction-related challenges that impede drilling performance while mitigating casing and drill pipe wear. WWT's NRP is a multifunctional tool with more than 30 years as a proven solution for reducing torque, drag, buckling, and heat checking, while protecting your casing and riser from preventable wear. WWT offers a no-cost confidential analysis with a recommended NRP proposal on your well, and 24/7 support both on and off the field.
All right, there you have it. Thanks to our wonderful sponsor, WWT. Like I said a minute ago, if you want to win the drill bit, you got to put in hashtag WWT. Not that hard. Go ahead and throw it in there. Let's see how many we're up to now. We're up to 29 so far. All right, guys. We've got over almost 100 people watching. Maybe now they're starting to come in. I think there might be a little bit of a lag in today's show. So, all right, let's do this real quick. We'll go ahead and hit present. I got to do my share screen Chrome tab because I didn't get this all set up beforehand. Share. There we go. Throw that one up on the screen. And we've got 30 people entered in. So let's see who the lucky winner is today. Here we go. So the lucky winner for today's Giant Gibson Reports drill bit is Brad Watson. That's 2 shows in a row. He won on Friday for the Vidor Locksmith show. And he won today. But that's what happens when you tune in and watch the show. You win stuff. So I've already got your address. I've already got all your information, bud. Nothing to worry about. We'll get that over to you. All right. Let's put this back up on the screen. And let's get our guest and expert of the day, Mitch Abahusayn from K&M Technologies. Thank you for being here, sir.
Thank you very much for having me, Dave.
All right. Well, I'll go ahead and bring your presentation up. And I'll turn you loose. This is all for you now, sir.
Okay. We're doing this live, so we're learning as we go. You are monitoring the questions as they come in, correct?
Yes. So for anybody that's got any questions, as they come in, I will be keeping track of them and starring them as we go through the presentation. And then once we get done, we'll be able to jump back in and be able to start. So I always forget to talk about, some of the things during these. So if you could reference either a slide number or just whatever the topic is, so that we've got a little bit of context as to what your question is about. So if you just say something about, something that Mitch might have said, then we're kind of might be guessing as to what part it might be. So give us a little bit of context, not too long of a question because it doesn't always show up on the screen fully, right? We might not be able to read all of it, but we will definitely go through and bring all of the questions in here at the end.
Okay, sounds good.
There we go.
So I think I called you yesterday about this talking. This was a lot more difficult than I had anticipated, just because there's so much stuff that we can talk about and we have a limited time. So this is typically stuff that we include in our training. We might spend like 5 or 6 hours talking about all these concepts that I'm going to talk about today. And we got to do it in like an hour and a half, or whatever that may be. So it's hard to give enough information. You want to give enough information to make sure that everybody understands what you're talking about. But at the same time, it needs to be meaningful information. I do teach some of these courses. Most of the engineers here at K&M do teach, and we do public speaking training. And one of the things that I learned is if you have 6 hours of material and somebody tells you you have an hour to do it, it's not great to just go in and accelerate how fast you talk by 6 times. so
it's not my Audible books.
No, that's not what I'm trying to do today. So if you are monitoring the questions as they come in, If you think that one of the questions is important to the context that either you or the public may be missing, I don't mind if you cut me off in the middle of my presentation and just say, somebody asked this thing and I think you might want to cover it now. If not, we can cover them all at the end. Again, it is your show. It's your world. We're all just renting space in it.
No, today is all about you, sir. It is your show. So, all right, I will let you, I'll turn you loose, and it's all on you, sir.
All right. So, what I am going to be talking today, what we said, this is week 6 or week 7. This is operation and design solutions to torque and drag problems. There's a bunch of them. So before I get into the solutions, we need to go back and just, in case nobody has seen any previous context, let's at least spend a few minutes just covering the basics. So one of the things that I think Brandon talked about in week 1 is just what is the force of drag. So drag is a normal force times your friction. That's it, right? And he also referenced somebody saying torque and drag and calling it drag and drag. Well, that is kind of accurate. So torque is just drag in the round and round direction. So you take your normal force times your friction, and you multiply it by your effective radius. Now, this is week 6, so hopefully you guys have gotten this by now. So there's a couple of ways that normal force is a couple of different things that contribute to normal force. One of it is just the weight of the pipe laying on the low side of the hole. Another one is the amount of side force that when you take something and you put it across a curve and you put tension on it. There's actually 4 total contributors to drag. There's that weight component. There's the tension component. Whenever you have it's called capstan effect. So if you have a curve, and let's see, let me see if this is in frame just so I can demo something. So I got I have a wire right here, and I think if I step back, maybe you can see the back of my chair, hopefully. So if I take this wire and I put it across the bend, if I don't put any tension on it, it does not push into the chair very hard. If I start pulling tension on it, you can almost see the fake leather of this chair start getting indented. So that's the normal force due to tension around a curve. Okay. And then whenever you put pipe into compression and it buckles, then that pushes into the side of the hole a little harder. And then one of the topics a few weeks ago was the difference between stiff string models and soft string models, and that's where they try to account for the stiffness effect. Pipe is steel; it's inherently rigid, so if you try to bend it, it does want to go straight. The most of the stuff that I'm going to talk about today is concentrating on these first 2 things: the weight component and the tension component. So let's just go back and see how to calculate that normal force. So the normal force is tension times your change in azimuth times the sine of your inclination squared plus tension times the change in your, I said azimuth here, hopefully, tension times change in your inclination plus the weight times the sine of your inclination squared, and then you square it, the whole thing. And it's like, whoa, that's just so many terms, such a long equation. So whenever I see an equation like this, I try to dumb it down. So let's think of some ways that we can dumb it down. Well, let's see if we're in a complete tangent section, okay? So no change in inclination, no change in azimuth. If there's no change in azimuth, that's 0. Anything times 0 is 0, so this term goes away. If there's no change in inclination, this is 0. That term goes away. So then you just have the weight of the component times the sine of your inclination squared and square root of it, which is the weight of the inclination times the sine of your the sign of your inclination. So if you are vertical, it would be completely 0 because the sign of 0 is 0. And if you're at 90 degrees, then it's the full weight of the component laying on the low side of the hole. And then between 0 and 90, there's some component to that. Okay, that's one way to dumb it down. What are a couple of other ways to dumb it down? Because what I'm trying, the reason why I'm going through all of this is it's important to understand what is driving this normal force, what makes normal force big and what makes it small, or why, or when it could be small. Okay. So anything in the horizontal section. So now forget about complete tangents. Let's say what parts of the well the normal force could be high, and what parts of the well the normal force could be low. So if your inclination is 0 or approaches 0, then the sign of 0 approaches 0, right? So if okay. So if you're in the shallow part of the well at really low inclination, then the sign of 0 is going to be a really small number. This is going to be a small number. So anything times 0, again, makes this term go away. If this term gets close to 0, then this goes away. And what you're left with is just tension times your change your inclination squared, and your square root of it. So what that tells you is when tension is high, then any small dog legs or small changes in your inclination is going to drive up your normal force. Where does that happen? Well, tension is always going to be very high close to surface, especially in deep TVD wells. Okay. We also we do a lot of teaching, so we get a lot of feedback from classes. And what we have come to learn over I've been working for K&M for 12 years now, 13 years now actually. But a common theme is drillers hate geosteering. They say, "Oh man, those dog legs. We were geosteering. We put so many dog legs in the lateral that's added so much torque and drag." Well, let's think about how accurate that actually is, right? In the lateral, if you're rotating off bottom, you have 0 tension in your string. So in places where you have 0 tension in your string, so if tension is 0, this goes away. And if this tension is 0, then this goes away. So basically it's your weight of your component times the sign of your inclination. Now, remember when we went back, we said that we're ignoring the stiffness effect. So this term is not completely accurate because the normal force could be a little bit exaggerated due to the stiffness effect. But one thing that we have learned is that stiffness effect is minor compared to everything else. Okay. So what are some problems that high normal force causes? One of them is obviously high axial drag. So not being able to run in hole or running out of weight. That could be with your drill string. That could be with casing. That could be with a liner. With a liner, if you're trying to run in the hole and you just can't get down to bottom, then obviously because a high normal force times your friction equals a lot of drag. Drag always acts in the opposite direction of motion. So if you are trying to run in the hole and you have high drag, it's going to prevent you from getting down to bottom. Well, it acts in the opposite direction of motion. So if you are trying to trip out of the hole and drag is really high, it might prevent you from tripping. Either with a drill string, you try to pull, you exceed the tensile limit of the pipe or whatever, tensile limit of the rig or the pull limit of the rig. So you try to do a straight pull and it doesn't work. And now you have to back ream out a hole just to keep my tension low. So it could prevent you from running in the hole. It can prevent you from pulling out of the hole. High torsional drag or torque. So basically, if you run out of torque, then you can't rotate the string. Another thing that high normal force will contribute to is if you have really high normal force and that high normal force is happening across casing, then it increases your risk of wearing out your casing or casing wear. So, and we've had situations where it degrades the casing wear is so bad that it degrades the casing and to the point where it can't hold pressure, and then you have to scrap the well. So that's a big problem. If the high normal force is in the open hole section, it can cause a key seating problem. And if you have a key seating problem, then obviously the pipe wants to sit in that key seating, and it can cause problems trying to trip out of the hole or trip in the hole. So I said we ran out of weight. So first, let's define what exactly do we mean by running out of weight, because we hear that a lot. And there's two contributors. There's two ways that you can, quote unquote, run out of weight. One of them is you just have a negative weight situation where the drag is so high that your hook load goes down and down and down and down, and then it's zero or less, and now you have to apply some push force to overcome that drag to continue to trip in the hole. If you had more weight available, then you'd be able to trip in the hole. So that's one. The other one is buckling. If you run out of weight because the pipe buckles, in this case, it's not going to run. It's not going to run down, even if I do apply weight. It's a frequent problem with drill strings. If you're running a liner, then the drill string you can run out of weight because the running string itself buckles. Smaller casing, anything that has a small OD it has less buckling resistance, so it's easier when you put it under compression that it starts to corkscrew and buckle. And when that happens, then supplying any more push is not going to help. And the onset of buckling can be very sudden. So it's really hard to determine if it is buckling itself or if it's some mechanical obstruction in the absence of some torque and drag modeling. So let me just show you a couple of examples. So this is an actual oil profile from up in Alaska, where they drill out and they make a huge turn. And what I'm going to do is I'm going to focus on this 9 5/8 casing down to 10,000 foot. So it's this section right here and this section right here. Okay. So 9 5/8 casing run down to about 10,000 foot and 12 1/4 inch hole. If you look at the slack off weights, this is what you would expect. So we have, the way that we model it is a fixed case hole friction factor, and then we vary the open hole friction factor. And in this case, if the top drive weight is 75,000 pounds, then anything higher than a 0.4 friction factor, and I run out of weight in this case. But what the modeling is telling me, assuming that the modeling is accurate and my prediction of buckling and the additional, if your torque and drag model actually accounts for the additional normal force due to buckling, what this is saying is if I could push with 100,000 pounds at surface, I could actually get the casing down for up to 0.6. And let's say that's my design factor. I've looked at some offset wells and I see a point, let's say I see a 0.5 friction factor. Well, typically what we do is we don't assume that we're going to have exactly the friction factor that we've seen on the previous wells, we put a little bit of a buffer in there, as drillers, engineers typically do, because you would always rather over-engineer something a little bit, and because the worst thing that can happen is maybe you spend a little bit too much time on it, too much money, but you get a successful well. If you're too optimistic, then the worst thing that happens is that, yeah, you have a well that's not successful. And, you know, depending on how big your organization is and how important that well is, then maybe that's an okay approach and maybe it's not. But let's say my design factor is a 0.6. I would need up to 100,000 pounds of push to get this 958 casing done. All right. This is a little bit confusing, so I'm going to step you back for a second. And the next thing that I'm going to show is this exact same hole here, but I'm assuming that, let's say I drilled a slim well where I set 9 5/8 casing here, and I'm drilling 8.5 inch hole, and now I'm running a 5.5 inch casing in it. This is what it looks like. So if I have 9 5/8 casing in here, you can see that if I apply about 15,000 pounds of push, maybe a little bit more, I can get down for a 0.25 friction factor. For a 0.3 friction factor, it locks up. And that's what happens when this shoots off to that's my left. I don't know if things get mirror imaged or not, but it's shooting off to this point over here. And if I went to negative 1 million, it would still go off to the left. What it's saying is it doesn't matter how much push I put on it, it's buckled and it's you know, it's not going to go. Okay, we're about 30 minutes in, and I'm just going through concepts right now. And the reason why I'm spending time on this is because it's really important to identify what the source of your problem is to come up with a solution that works. So, again, I'm going to go back, and these are important equations. So I'm going to show them multiple times. Remember that the drag force is normal force times friction. Torque is normal force times friction times your effective radius. So effective radius is the radius of whatever is in contact with the wellbore. Okay. And then this is the normal force equation again. So if my drag force is unacceptable, there's a couple ways that I can go about trying to find a solution for that. The first one is just accepting that drag is what it is, and I'm just going to have to overcome it. That only works if you have a negative weight solution. Like I said, if you have so much compression that you have buckling, you can't just overcome that drag. Okay, so that works for a negative weight solution. The other thing that you can do is, if you want to reduce your drag force, then it's two terms multiplied by each other. So one thing I can do is try to reduce my normal force. The other thing I can do is try to reduce friction. If I reduce either one of these, then my drag force is going to go down. The other thing I can do is change its direction. Brandon talked about this early on, and we'll discuss it a little bit more here. So if I have a lot of axial drag, can I change the orientation of that drag from axial drag to torsional drag? So let's look at the solutions for negative weight. Provide additional push to overcome your drag force. In drilling, for the longest time we were drilling with motors. Rotary steerable was not a thing. With motors, you typically have some amount of heavyweight drill pipe in the low angle section of the well. That provides two purposes. One of them is it's a heavy component that overcomes the drag in the lateral part of your well, so you can overcome that drag and push down. The other thing that your heavyweight does is it transitions the pipe from compression to tension. And if you have tension in your string, you can't have buckling. That only works to a certain point, because if you have so much drag in your lateral that it buckles, then having heavyweight drill collars, whatever, in the vertical section is not going to help, and you're not going to be able to drill with a motor. So I started in '98. Just to give you a little bit about my history, I went to the University of Colorado, go Buffs. And when I graduated, I worked for Aramco back in '98. A lot of the drilling was with motors. Rotary steerables were around, but people weren't using them a lot. And the guys that would come in and try to sell you rotary steerable was always that it's an ROP improvement, that you don't have to slide anymore, so your overall ROP increases. Okay. Well, I left Aramco and I worked for Maersk Oil in Qatar, where they were drilling really shallow, long reach wells. So it was at 3,500 foot TVD, and we drilled at the time a world record well of 40,000 foot measured depth. So it was a 35,000 foot open hole section. In their early wells, because they started drilling them before rotary steerable, they would just drill with an adjustable gauge stabilizer, because you had to rotate all the time. You couldn't put any heavyweight in there to drill with a motor. The only thing that you could do is put an adjustable gauge stabilizer, and depending on by manipulating the flow, you can make that stabilizer bigger or smaller, and make it a dropping assembly or a building assembly. So you had inclination control, you had no azimuth control. And then rotary steerable came around, and now we have inclination control, we have azimuth control, and we're rotating all the time. So the rotary steerable was developed to be able to drill wells that could not be drilled conventionally. It was a necessity. If you wanted directional control and you wanted to be able to rotate all the time, then you had to have rotary steerable. An increase in ROP, that was like an added bonus. But for some reason, that was the thing, because a lot of people were drilling with motors, and they just wanted the increase in ROP. But that seems to be the marketing focus, was that RSS, rotary steerables, increase your ROP. Okay. That's with a drilling assembly. With casing, you could run heavier casing, just like you have push pipe, or I think Brandon Foster corrected me. People define push pipe differently. I've always talked about the heavyweight itself as push pipe. Brandon said that it's the pipe that's being pushed is the push pipe. However you want to talk about it, that you need something heavier on top. So you have heavier casing on top as to push the lighter casing down below. The other thing you could do is use the weight of the top drive. Normally, when you run out of weight when you are running casing, that will happen typically at 3 a.m., maybe on a weekend. So this is something that you want to talk about with the rig contractor before you actually use the weight of the top drive, because a lot of the rig contractors, they're not used to using, their some of the weight of their traveling assembly to push pipe. So this is a conversation you want to have in advance. And usually you can work out something to say, okay, well, my block weight is 70,000 pounds. I'll let you use 25,000 pounds, 30,000 pounds to push. So you can use some of the weight of your top drive. Up in Canada, they have pull down systems, because they're drilling like the SAG-D wells, ultra shallow wells, where you run out of weight really quickly. So they have systems where it actually pulls the pipe to the rotary table. So you can have that. That also overcomes a drag problem. one thing, when I told you in my previous life, I worked for Maersk Oil in Qatar. That got bought out by Total, and now it's a company called North Oil Company in Qatar. But in some situations, when we were running the 958 casing and we got really close to the landing point, but we ran out of weight, we'd just rig up a false rotary table and put a retrievable packer in there and hang with some drill collars hung below it, just to supply some extra weight inside the casing. So you might have, so we showed these drag plots. This is the drag plot that I showed with the 958 casing for that Alaska well. These dotted lines are how much drag I would expect under normal conditions. If I were to go in there and say I ran 10 stands of 6 3/4 inch collars and I hang them, with a retrievable packer, I get an instantaneous increase in weight as soon as I install that. But now that packer is, right when I install it, it's right below the rotary table. But as I go in the hole, as soon as that gets into the higher angle part of the higher angle section of the well, it starts adding drag. So if this were to go a little bit further, I'd have to go in there, retrieve that retrievable packer, pick it up, and set it in the vertical section again. So it would require repositioning the drill collars if they enter the high angle section. The other thing you can do to reduce your normal force is to reduce the dog legs in the shallow section of the well. You can reduce the dog's legs in the shallow section of the well. You can reduce the weight in the high angle section of the well, or have it, we'll talk about floated casing here in a minute. And this is a possible solution for both the reducing weight in the high angle section of the well is a possible solution for negative weight and buckling, because if I reduce my normal force in the high angle section of the well and that reduces the drag to the point that I don't buckle anymore, then that solves both issues. So we talked about why the reducing the dog legs in the shallow section of the well, because when my angle is if my angle is very low, then the amount of normal force is very dependent on tension and how much inclination change I have. So that some people have thrown this term around, the whole pseudo catenary curve or a catenary curve. What is a catenary curve? So here's an example well where I have it's a fairly deep TVD well, 14,000 foot, and I have a shallow dog leg here. In this the blue line is a 45-degree well with a 3-degree buildup. The red line is a well where I'm gradually increasing my build rate to build a catenary curve. What is a catenary curve? It's what's called the perfect curve. So it's your side forces are normal or equal throughout the curve. You don't have higher side forces and then lower side forces. The side forces are uniform. It's how umbilical cords are hung, like the shape that an umbilical cord that's hung or arches. See, I got a little prop right here. It's just a wire that I grabbed out of one of the offices. If I have my surface right here and say this is the downhole location and I'm holding the wire, you can see that is not a uniform curve. It's not like a fixed build rate from surface here down to bottom. The build rates are lower here and they're higher here. Why is that? Because the perfect curve means that normal force is constant throughout. How do you get a constant normal force? Well, at surface where tension is the highest, then my dog leg has to be the smallest. And as I go down and down and down and down, and tension gets smaller and smaller and smaller and smaller, then my change in inclination or my build rate can get higher and higher and higher. Okay. The reason why I'm bringing this up is because I've seen people hear the term catenary curve, pseudo catenary curve, and what they'll do is they'll say, "Oh, okay, I like low normal forces. I want to solve this problem. I'm going to put a 300 section where I'm building at 1.5 degrees, and then I'm going to put a 300 section where I'm building at 2 degrees or 2.5 degrees, and then I'm going to put a 300-foot section where I'm building at 3.5. Check the box. As I go deeper, inclination is increasing." Well, to properly, I'll get back to this. Well, okay. I guess I'll talk about this now. What I'm showing here is the amount of torque generated for different friction factors with a 3-degree build and hold at 45 degrees. And I have this light blue shaded area. Say it's right around 30,000 or 30,000 foot-pounds of torque, which is right around the makeup torque of 5-inch drill pipe. All right. So if I had that well, I would not be able to drill with 5-inch drill pipe unless my friction factor was less than 0.25. Anything higher than that, and it's a problem. And then, the red line is the build and hold for the 3-degree build and holding at 45 degrees. These curves that I'm showing now is this catenary curve that I'm showing right here. So you're looking at this and it's saying, okay, well, with a 0.3 friction factor, I'm right around, call it 41,000 foot-pounds of torque with a straight build and hold. I've dropped it maybe 1,000 foot-pounds for a 0.3 friction factor with a pseudo catenary curve. And God, it was a lot of effort. I had to go in. I'm putting, a schedule of increasing my build rates. Was this really worth it over 1,000 foot-pounds of torque? Well, if you look at the normal force that was generated by these two different well designs, so the blue is a buildup rate of 3 degrees and then holding at 45. The red is starting off like right around 1.25, it increases to 1.5, and then it increases to 1.75. And this is how you would properly design a pseudo catenary curve. So you would look at, you may know, so you should, if you're observant, you might see that on this graph at 2,000 pounds of side force, anything higher than that is shaded in gray. Why is that? Well, because at higher than 2,000 pounds, then casing wear does become a major concern. It's not to say that you're always going to have a casing wear problem if you have more than 2,000 pounds of side force, but it increases the risk quite significantly. It'll depend on the hard banding. It'll depend on how high above 2,000 pounds. It'll depend on the formation that you're drilling. It might even depend on the mud that you're running. But if you have less than 2,000 pounds, one thing that you can be comfortable with is your risk of casing wear goes down significantly. So you would design this well to say, okay, well, I have to kick off here. The first thing you'd ask yourself is, do I really need to kick off that shallow because the tension is so high? Let's say that well is is on an offshore platform, and you have a lot of slots on the platform, so you need to get away from other wells. So you do need to kick off very shallow. Well, then you say, okay, what is the maximum dog leg that I can have before I exceed 2,000 pounds? And in this case, it's 1.25. So that's what you would set. And then you'd hold that until your next step change in dog leg gets you back to 2,000 pounds. So you're going to hold that all the way until this point right here. And you say, okay, well, I'm going to go up to 1.5. And at that point, it's at 2,000 pounds again. And then I'm going to hold that until my next increase in dog leg gets me back up to 2,000 pounds. So that's how you would design the catenary curve. Keep in mind that these dog legs are perfect. So directional drillers are kind of programmed to be ahead of the curve. It's something that's just ingrained into them. Kick off early, be ahead of the curve. It's a lot easier to drop back down to the curve than to catch up to it. So if you're doing something like this, then it's worth talking to the directional company and being like, listen, man, I put a 1.25 degree dog leg in there in person. What I don't want to see is a 3 degree just because you were eager to get kicked off early. So they need to understand why exactly you're designing the wall like this. Okay. See, I've worked with people that like U.S. land type wells, where it's just, you drill down to just the kickoff. You're planning to drill a 10 degree, and people say, "Yeah, but I'm worried about torque and drag. I'm gonna kick off at 6 degrees, and then I'm going to increase it to 8, and then I'm going to increase it to 12 or 14 degrees and land the well that way." Well, if you think about it, that last 1,000 for the deep part of the well, there's very little tension there. So putting a catenary curve, replacing a constant build rate in a U.S. land type unconventional well, where instead of building at a constant 10 degrees, you build at a lower and then increase it. You're not going to get the same bang for the buck that you are here, just because there's not a whole lot of tension down deep in the well. At least when you were tripping in. At one point, like if you're drilling a super long lateral and you're pulling up, then yeah, you're going to have all the drag, and there's going to be a lot of tension across the build section if you're trying to straight pull. Okay, so we talked about reducing the dog legs. The other thing that you can do is remember that this is all tension driven. The side force is tension and dog leg driven. So the other thing you can do is just run lighter drill pipe. We've worked on projects where we have run aluminum drill pipe. So aluminum drill pipe, very light. If you have very light drill pipe, tension is low, the side forces are going to be low. Casing flotation. This may seem silly, but I feel like I have to say it out loud, because there's always a couple of people that I come across that think floated casing is like, if I have, this drawing right here shows mud-filled casing, and then there's some baffle system that isolates the bottom of the hole, and then the bottom of the casing, and this casing here is run empty. So under atmospheric pressure, you're not filling it with any fluid. Because it's called casing flotation, there's always a few people out there that think that the casing is, I'm going to adjust my camera just a little bit just to make sure that if I'm using my hands, that you actually see everything. There's always a few people out there, when you say casing flotation, the casing is actually floating and on the top side of the hole. That is not the case. You do not want casing that's actually positively buoyant, because if casing is positively buoyant, you would push it in the hole. I think anybody that has cemented surface casing, or a conductor, surface conductor, sometimes you cement surface conductor and you actually have to chain it down so the casing does not float out of the ground before the cement sets up. Well, if you run in with, say, 9 5/8 casing that's positively buoyant, if you ran it in the hole, to chain it down if it was positively buoyant to keep the casing from shooting out of the ground. So you usually it's you don't want the casing to be positively buoyant. You just want to reduce its adjusted weight. And there's a couple ways to do that. You could either run the casing completely empty, or you could put this kind of baffle system. Davis Lynch used to have like the market on this, but now there's more providers. It's just some way to isolate the bottom of the casing from the top of the casing, so you can fill the top of the casing with fluid. And if you have mud-filled casing up here and air-filled casing down here, it is like having, a lot of weight up here that overcomes the drag down below. How buoyant is the casing is very dependent on mud weight. Normally when you run casing, the buoyed weight of the casing is hardly even noticeable if you were to go from like a 9 to 9.5 to a 10-pound mud. That most of a calculation where you go in and you figure out what the buoyed weight of the casing is, that depending on the mud weight. But when you are running that casing empty, if you are running that casing empty, now it is very dependent on the mud weight. Each casing size and weight is going to have a critical mud weight where if you run a mud weight lower than that, then it will be positively buoyant. Some ways that you can overcome that is maybe fill a portion of the casing just to make it a little bit heavier, but then it's kind of defeating the purpose, because the point is that you were trying to make the casing light. Now it's too light, so now you're filling it with mud again. It becomes pretty complicated. So you want to plan your casing run for the full range of the mud that you're going to use. And when we talk about that, each casing has a critical mud weight. So this is typically limited to 9 5/8 and smaller casing when you're floating. There was one case that we evaluated that I can think of where we ran. It was not for a deep water environment. It was offshore, but they were planning on using 13 and 5/8 88-pound casing just to keep it from being positively buoyant. So let me just walk you through this graph, this table a little bit, show you what it's, explain what it's showing. So I have 9 5/8 casing. The air weight of it is 40 pounds per foot. If I run that in 9-pound mud, the casing feels like the adjusted weight has reduced to 6 pounds per foot, that's massive. That's an 85% decrease in the weight of your casing. If you run it in 10-pound mud, it's 2.2. If you run an 11-pound mud now, so any of the red numbers means that it's positively buoyant. It means that you would shove that casing in the ground, and if you did not hold it down, it would shoot back up again. So 40-pound casing, you're limited to less than 11 pounds. So you could run 47-pound casing. But at 47-pound casing with that same range of mud weights, you can see that you're not getting the same bang for your buck. The easiest thing to do to calculate what the buoyed weight of the pipe is to figure out how much volume that's displacing, what is the weight of the casing, and what is the weight of the fluid that you're displacing. I mean, that's in the simplest terms, that's how you calculate buoyancy. If I have 1 cubic foot that weighs 5 pounds, if I put it in a fluid that displaces, if it displaces 5 pounds, then it'll sit completely neutrally buoyant. It won't float. It won't drop. If I put it in there and it displaces fluid that's more than 5 pounds, then it's going to float. If it displaces fluid that's less than 5 pounds, then it's going to drop. Okay. And that is why for the 4.5-inch casing, 4.5-inch casing, the air weight of it is 13.5. If I run it in a 9-pound mud, the air weight of it is actually higher than 40-pound casing in 9-pound mud, because the volume that 4.5-inch casing is displacing is smaller. So the reduction is smaller in smaller casing sizes. So kind of the sweet spot for it is right around is the 958 casing. That's where we see it floated casing happen most often. You can do it with 7-inch. You can do it with production casing. We're doing it quite a bit here in the U.S. But once you get above 9 5/8, it becomes very difficult. Another thing to point out that's important is these baffle plates. So if you run air and then you run mud above it, it's not to get this thing to shear, you have to apply some pressure to get it to shear. The amount of pressure that's applied to get this to shear is an absolute pressure. It's not a differential pressure. So whoever is providing this, whether it's Davis, Lynch, or Halliburton has one that called the buoyancy assist system, I think. NACE has one also. What they're going to want to know is how deep TVD wise when you plan to rupture this, how deep TVD will it be, and what is the mud column that you are filling the casing with. And the reason why that's important is because the mud column is going to provide some level of pressure, and then you need to put an additional pressure to get that to shear or fracture. And then once you do that, the mud swaps and this mud will come down to the void. This void will percolate up. Typically, that's how you want to do it. You want the air to come out from inside the casing. You usually you install a cement head because it can be a lot of bubbling at surface, and you want to route that back to your active system to capture any fluid that's bubbling back, and then you fill your casing. There have been some operators that they get down and they just rupture this disc and they start circulating the long way. Now, keep in mind that the air in this void is under atmospheric condition. So if by the time you're set, if your casing is at 7,000 foot, it's under significantly higher pressure once you rupture that disc. So this large volume, that air volume inside the casing is going to get squeezed and become a very small volume. But as you circulate so if you circulate it out the long way, when that's in the annulus here, it's going to be fairly small, but it will start expanding rapidly, just like a kick does at surface. So I was talking to somebody that was, it circulated it the long way. I said, how did that go? And he goes, well, the annulus got a little violent. So they continued to do that on future jobs, but then they went through the choke. It's probably a little bit more risk than, I would want to take, but to each their own. So some things that you need to consider if you plan on floating casing. Hole has to be very clean prior to attempting to float the casing, because when you float your casing, remember, this is a void filled with air. If this is a void filled with air, that does not allow, you cannot tag something and say, well, I'm just going to wash through this. It's not going to work. Once you fill your casing, you're not floating anymore. That a lot of time that ends your cement job or your casing job. Delta Tech, however, does offer a solution to float casing and be able to circulate it, including during the cement job, which is pretty interesting. You might want a casing running tool to facilitate either pushing or reaming the casing, because it is very close to neutral. So we're not even going to talk about hydraulic lift effects, but when casing is close to neutral, the pushing the fluid out of the hole causes some hydraulic lift. So just the fact of tripping in the hole causes some hydraulic lift. Normally, that's not noticeable under a traditional casing job, just because you have so much tension at surface. But when you're only working with 10 or 5,000 pounds or 15,000 pounds of positive tension while you're running your casing, now some hydraulic lift becomes very noticeable. You also need to be prepared if that casing collapses. So if you have a connection leak or if your casing collapses, the mud is going to go down the annulus to fill that void inside the casing. So you always want to be lined up to fill your casing. Fluid logistics is a big one that people may not consider. If you run one joint of 9 5/8 casing in the hole, you displace roughly 4.5 barrels of fluid out of the hole. 4.5 barrels of fluid, that's a lot of fluid for each joint of casing. Normally, we don't even think about that, because that fluid that's coming out of the hole, we're using that to fill the casing. But if you're floating the casing, that's not going back in the pipe. So you need some place on your rig to store to store all of that fluid, because you're not going to put it back in until the very end. At the very end, you're going to fill your casing or liner when it's at the setting depth, and that can take a lot of time. So you need and patience, because it is a slower operation. So all of that so far. So we talked about one of the different ways that I can reduce drag. The other thing is that I can reduce my friction. How do I can do that? Probably the easiest thing in our experience is just to increase your annular clearance. One of the main drivers for how high that, remember that mu or coefficient of friction, that's not what we're dealing with. Like we put in friction, we substitute that with friction factor in all of our calculations. And we've noticed that the more annular clearance you have, the higher the friction factor. And I think that may have been some of the debate a couple weeks ago when H&P was talking about the necessity of a stiff string model. You know, we run a soft string model. I don't want to debate which one is more accurate. The only thing that I would point out is every time you reduce your annular clearance, friction factor, your friction should increase, or we have seen the friction increase regardless of if you're using a stiff string model or a soft string model. So if you were to drill 12 1/4 inch hole with 5-inch or 5.5-inch drill pipe, even if we were to use a stiff string model, when you run 9 5/8 casing, you should fully expect to see higher friction factors when you're running 9 5/8 casing inside a 12 1/4 inch hole. So you can increase your undering the hole, make the hole bigger, put your completion or your casing smaller. There's a drive in the industry to slim down wells, like it's the cost of the cement that's really driving the economics of our wells. There's a lot of downside to having really tight clearance that we prefer to avoid. Other thing you can do is add lubricants or beads, anything to reduce your friction. Some of them do work. What I will say is, before you rely on any lubricant or beads or anything that claims to reduce your friction, try it on a well that does not require it, and make sure that you actually do observe that reduction in friction factor and that it is repeatable. Because friction factor is not coefficient of friction. So there are some lubricants where in a lab it will reduce your coefficient of friction. You add it to your mud and it does not do anything to reduce your friction factors. So I would not design a well based on, you know, that, hey, this product that I'm going to add is going to reduce my friction. You can also have some mechanical tools like bearing, roller, low friction centralizers. So let's talk a little bit about those. So here's some examples, I guess. So, you know, low friction centralizers. Just keep in mind that if you have high normal force, so that's a lot of load on these. And if these are not steel, are they going to be able to hold up? And again, I would want to make sure that I try these on easier wells. Another thing, so Western Well Tools, they're sponsoring today's event. You have you know, these non-rotating drill pipe protectors. So this is not going to reduce your normal force, but it will reduce your friction. It will reduce your friction and your torque in a couple of ways. So I do have the video. So you want the non-rotating drill pipe protector, you need to install it very close to your tool joint. The idea is that you provide some standoff of your tool joint. I've seen people order these and then install them mid-joint. If you're installing them in the middle of the joint and then your tool joint is still in contact with the side of the hole, they're really not working the way that this should be. The idea is you want this to become not to be touching the side of the hole. And when you do that, you reduce your torque in two ways. Normal force hasn't changed, but now you have a mud bearing between the sleeve and the pipe itself. And remember in that equation that the rotational drag or torque is normal force times friction times your effective radius. Well, if this is 5-inch drill pipe with 6 5/8 tool joint, your effective radius normally is half of 6 5/8. And now it's the effective radius is half of the diameter of the 5-inch drill pipe. So your effective radius has gone down, and now you have a fluid bearing also where this is rotating inside of it. So these do work. You just want to install them in places where the normal force is actually high. We've seen people try to run these in the bottom of the well because like everybody thinks that the casing is, or the drill pipe is laying on the low side of the hole in the high angle section. So that's where all my torque is coming from. So if I install these, it's going to do a great job at reducing torque. But remember, your normal force is actually probably not the highest down there. It's the highest shallow, where you have your highest tension is, where the highest tension is, and where the biggest dog legs are. Some roller options. So these got one of these also. These things are heavy. These things are heavy. So these are bidirectional rollers. You would install them on casing. And I don't even know if they produce these anymore, honestly. But I still want to show them to you so you can see how far those rollers are protruding out. So these rollers are axial rollers, so they're intended to reduce drag. These rollers right here extend internally, so your casing rotates inside of them and they reduce torque. So these are bidirectional rollers. They're heavy, they're expensive. It's been a long time since I've seen somebody use some of these, especially with the increased instances of people floating casing. That tends to be the preferred option. That's a lot easier now, or just reaming casing down that's mud filled if your torque can handle it. The reason why we typically float casing is well, we'll talk about reaming here in a second. In 958 casing, the weight of the casing is so heavy that it becomes difficult to rotate it down. Smaller casing size, sure, you can. These are what I'm showing here on the right is anytime you run a completion that has hydraulic lines, that has fiber optic lines, something that prevents you from rotating it, this is where we currently still see them. So you see here's a clamp with rollers on it. Notice how big the clamp is, because this needs to be sized to the size of the hole that you're running it in. If you put it in too large of a hole, then the thing just kind of flops over on the side. You need these rollers to be actually acting on the casing. If they're not acting on the casing, if the thing just flops over sideways and it's dragging along here, there's just not going to be any benefit. So this is where rollers for casing, these types of rollers, pretty uncommon. Haven't seen them in a really long time. The instances of us seeing them is actually increasing. And just like what we said about lubricants, well, a couple things need to happen. One is that your casing needs to be incredibly clean. Look at how far that that wheel is extending. So if you have a cuttings bed or any amount of dirt in there, then that wheel is not going to help you out any. So your casing that you're running this in has to be incredibly clean, for one. The other thing is I would like to document that I am actually getting how much of a drag reduction or reduction in friction am I seeing. We've seen some of these have a fairly decent reduction in drag in the larger size hole. We're just looking at a case a few weeks ago where it was like 3.5-inch tubing, I believe, inside 7-inch casing, where it was still a 0.35 friction factor, which is much higher than what you would assume if you had, ball bearings. Just on the topic of bearings, this is similar to the Western Wall Tools one, but it's a sub, so you probably only install one of these per joint. So the other two joints are still going to be in contact with the side of the hole, but because this is steel, it can take a higher side load. The Western Wall Tools ones, there is a fixed limit of how much side load one of these can take before you exceed its loading, and then you have to install multiple ones to keep it within spec. Like I said, it's a shotgun of information. This is a lot of information in a short period of time. The last part that we talked about, so we talked about reducing normal force. We talked about reducing friction. We also talked about, some ways to overcome it is change its direction. So remember, if I am running in with a liner, then drag is always in the opposite direction of motion. So right here at the float shoe, I don't have any drag, and it's in the opposite direction of motion, and it's an accumulative effect. So drag gets higher and higher and higher and higher and higher. So I get more and more and more compression as I come up the string. And in this case, let's say the compression has gotten so high that I have buckled my string. So that's when I'm trying to trip in the hole. Now, if I stop, say I pull it into tension first to get rid of that buckling. Now, if I just stop right there, and this is a completely horizontal wall, if I sit there and start rotating, then I have no compression, no tension in the lateral, and all I have is torque. Okay. What about if I'm tripping in the hole? Yeah, this one. So if I'm sitting there and I am rotating, at say 20 RPM, I get a certain amount of torque. Now, when I'm running in the hole, the drag is bidirectional. I have some of it in the round and round direction, some of it in the up and down direction. How much of it is in the round and round direction and how much of it is in the up and down direction, I have full control over, which is a yay moment. There's a lot of stuff that we don't have control over. The fact that we can manipulate how much drag we have based on our operational practices should be something that we celebrate. So what you just run this again, 20 RPM, I end up with a certain level of torque, and now I'm tripping in the hole. You'll see that I'll get a lot of compression at 20 RPM. Now, if I increase my RPM, then my compression load will go down because more of the drag is in the round and round direction. How much of it is in the round and round direction and how much of it is in the axial direction is it's really just vectors. So I have this V sub A is my actual axial velocity. So this is how fast I'm tripping in the hole. V sub C is my round and round velocity, circumferential velocity or round and round velocity. If I had, say, I think on here there might be, if I put a dot on one of these casing collars, and I wanted to see what was the overall velocity of that dot when I'm reaming, that's what this is, that resultant velocity. Because it is going round and round, and it's also going up and down. So how do I calculate the total velocity on that casing collar? Well, you take your axial velocity squared plus your round and round velocity squared, and you square root it, and you get that's your total velocity. V sub C is pi times d, the diameter of the hole. This is just because normally we talk about tripping speed and feet per minute. So and the diameter, we usually talk about that in inches. So if we're talking about, if we want everything to be in feet per minute, that 12 is just a conversion factor from inches to feet times RPM, how many revolutions per minute. So V sub C will go up. If your RPM goes up, it's also very dependent on the diameter of your casing. The diameter of your casing, like 958 casing, has a huge circumference. So you rotate that at 10 RPM and it's moving 20 RPM, it's moving fairly fast. If I take a very small tube and I rotate it at, so talking about 3.5, 4.5, if I'm rotating that at 20 RPM, 30 RPM, the circumference of it is so small that the velocity around the circumference is very small when I'm rotating at a low RPM. So small pipe would require me to rotate faster. Larger size pipe, I can get away with rotating at a lower RPM. And then basically you take your axial velocity divided by your total velocity, and that's how much you're going to reduce your axial friction by. And you'd substitute this into your drag equation. Most programs will do this automatically. I'm just showing you how the torque and drag programs work and how you're seeing it at surface. A lot of times I try to bring it back to people when we go out and we record torque and drag data. One of the critical inputs for us, or the stuff that we track, is pickup weights and slack off weights. I can't tell you how often people have recorded the reaming up weight and the reaming down weight as their pickup and slack off weights. That is horribly wrong. And the reason why is because when you're reaming up and down, you can make that number whatever you want depending on your parameters. And don't take my word for it. Just go out to the rig and try it. Drill stand down, rotate at 20 RPM and trip out fast and trip in fast and see how much fluctuation there is in your weight indicator. And then drill stand down, stay rotating at 120 RPM, and trip at 1 foot per minute. And your rotating weight will not change. So based on your RPM, based on your trip speed, you can make your weight whatever you want it to. And if you really want to overcome drag, if you have a drag problem, you want to reduce it, then higher RPM, slower trip speeds are the way to do it. And it's getting close to 9:30. Getting close to 9:30. We got about another 10 minutes and got a few slides. So, from a rotational requirement, when the string and your top drive need to be capable of that of the required torque. And then with a large size casing, because the moment arm the casing is heavy, that effective radius is big. So between both of those, your torques tend to be really high. So in large size casing, 958 casing, it almost forces you to float it to be able to rotate it. In smaller size casing, 5.5 inch, you might be able to run it conventionally, mud filled, and be able to rotate it depending on your capabilities of how high the torque rating is of your connection. The other thing that is important to note is that the contact points between the string and the hole need to be rotating. So if you're running centralizers, then those centralizers need to be fixed for rotation to be effective. Here's some different, there's the centralizer subs, wear socks. This is, this was developed ages ago where it's just applied to it. I think Halliburton has something similar where it's applied to the casing. More and more, there's these, I think I got, so there's these kind of things where they're, kind of like epoxied onto the casing where you can make your centralizers whatever shape you want them to on your casing, which is interesting. Volant, Tesco have these hydroforms that are crimped on. Unique Machine has, so this would replace your coupling. Instead of your coupling, your coupling would be the centralizer. All of those are, the intention is that they're fixed. When you rotate your casing, the centralizer rotates with it. So it allows you to be effective when you're reaming it. Now, I'll also give you some hints of typically these are less convenient than your standard centralizers because those are easier to find. They're typically more expensive. So some people don't like running the fixed centralizers. So if you want, let me be absolutely clear that what I am for, what K&M's for, is for good centralization that provides good standoff throughout, right? If you as an engineer or a superintendent or an organization just said that that's an inconvenience that I'm not willing to accept and I don't want to do it. Okay. Well, one thing that you can do is you can run free floating centralizers, but run them at a frequency where you have zero standoff on purpose in between the centralizers. And we've seen this we've seen this done in U.S. land where it's unconventional. You're doing a lot of frac stages. You just want a cement plug, good isolation in between your frac stages. So if your frac stages are, say, for shits and giggles, every 120 foot, every 3 joints, put one centralizer on. So in between them, you're going to have zero standoff and you're going to get the benefit of rotating your casing down there. Where the centralizer is, you're hoping that at least provides a good enough cement plug to isolate frac stages. Swivels is another thing that allows you to rotate one part of the string, and then not rotate the other. for them to be effective, you need to have high drag across the part that you're rotating. Now, I realize, somebody showed me this, so I'm going to try to use it. I learned something new. So if I go in here, zoom in, boom. So in this type of well, if this say it's 3.5-inch screens, that would be an application where a swivel would make sense, because I could let's say I have a screen that I do not want to run the screen. There are screens that are rotatable, but let's say it's a conventional sand that I'm drilling. I want to run screens. I don't want to rotate my screens for whatever reason, or maybe the screens that I have, the connections don't allow for it. I could run a swivel and eliminate or reduce the drag throughout this entire section of the well. Very different than a U.S. land type well. So if this was 5.5-inch casing, then that's fine. But let's say this is 5.5-inch liner, and the top of the liner is right here. Well, I have very little drag from here to surface. So in this type of well, running a swivel wouldn't make any sense at all. A couple of different, so you can have a swivel either for your drill pipe, where it allows the bottom section is not going to rotate, the top section will. Now, lately, there have been casing swivels. Personally, I haven't run them. I know that they're out there. So what would be the advantages of having a casing swivel? Well, let's say you want to rotate your casing during a cement job, but the torque is too high. Well, you can typically the bottom of close to the float shoe, you typically have good cement. It's the cement that's further up the hole that's more compromised. Well, maybe I install a swivel halfway through my casing, and I rotate a portion of my casing and get good cement. Yeah, I don't know. Like I said, I have not used these, because I came from, when I was working from Aramco, we ran DVs, multi-stage tools, for the cement job on every single well. And then I went for Maersk, and they were like, we would never run a DV tool or a multi-stage cement job, because we don't want to put holes in the casing on purpose on day one. So to me, I mean, it's a bearing there. I don't know. I haven't had any experience with it. Just like I said, I'm just throwing out what information we have and what is available right now. Some programs allow you to model a swivel. Some programs don't. If you have a program that does not allow you to model a swivel, just model the section of the pipe that's rotating, and then model how much drag is being generated by the section that's not rotating, and make sure that you can apply that amount of weight on bit or push at the swivel. That's all you're doing, really, because if the bottom of the string is not rotating, then you have drag there. And the top of the string that is rotating, it needs to be able to push and overcome that. So effectively, it's a weight on bit at the swivel point. So that's how you'd model it if your torque and drag software can't do it. If it's not built into the program. But some, either if you have perforating guns, if you have screens, if you're exiting across a whipstock from a casing and you're worried about damage to anything, maybe you run it then. The normal drill pipe swivels, those you retrieve back to surface. The casing swivel, that's sacrificial, obviously. So that stays with the casing. And then the last thing to keep in mind with a swivel is that it is a bearing, and it's a bearing under a certain amount of load. So it's going to have some limit on that bearing life, depending on the compression load. The higher the compression load, the lower the number of rotations you can apply before the bearing fails. So it's just something to be aware of, that if you're using a swivel, that does have a limited life depending on what the compressive load is and how much rotation you're planning on doing. And I think this is my last slide, and then we'll open it up for questions. We haven't even talked about cementing yet. One of the best things you can do to ensure that you get a good cement job is to rotate either your casing or liner during the cement job. It's something that we have a very poor track record at being successful at. And why is that? Is because you run your casing, you run your liner, you see a certain level of torque, and then you start pumping your cement job, and that torque is not constant. It may go up, it may go down. Right when it exits the shoe, it might spike, the torque might spike, and people start freaking out. Like, no, nobody wants to twist off. You've done all the hard work. You're at T&D, the casing's there, you're just trying to cement it. So it's very easy to just say, like, no, I'm not going to do this, and shut it down and just, be done with it. So what we do is we model what the torque, so if this was a liner, this is the torque at the top of the liner. This is the torque seen at surface during a cement job. And it doesn't matter. It doesn't really matter what the well looks like or what the well profile looks like. It's just as you are pumping cement, as you're displacing fluid down, notice how the surface torque does fluctuate. So as you pump, typically cement is heavier than the fluid, than the mud that's in the hole. So when that cement is going down your casing or down your liner, notice how torque is probably going to increase. Again, it'll depend on your well profile, but it's not uncommon for it to increase because your casing is getting heavier. Now you have your steel plus a heavier fluid inside of it, so your normal forces are going to go up. So if your normal forces go up, your torque goes up while the cement is inside your casing. Maybe you have a water pill or a diesel pill in front because you're worried about cementing ECD. Well, when that light fluid comes outside, if there's light fluid outside and heavier fluid inside, your torque is going to go up. When that light fluid is inside the casing, your torque is going to go down. And then what we do is once the cement exits the shoe, any place that there is cement, we call it cement friction factor, and we substitute the open hole friction factor with the cement friction factor. And it helps explain why we see what we see, because cement, it's viscous, typically. It's loaded with solids. So it's not a stretch to say, well, yeah, the friction environment is going to be different where they're from the cement compared to where it is with the mud. So we just put a new friction factor in wherever there's cement in the annulus. And what we're hoping, like when we're tracking one of these jobs, is that we're just going to see torque follow one of these lines. So torque may increase and then it might become stable because now you have heavy cement on the outside, you have lighter fluid on the inside, so now the casing gets lighter. So the casing gets lighter, your normal force goes down, but the cement is viscous and loaded with solids, so maybe it has a higher friction, so maybe the friction goes up, but normal force goes down. I don't know in advance, but once you do a couple of these and you kind of see what you're tracking, then you can use it to monitor future wells. So that is over an hour and a half. I think that is my last slide. So that is all I got.
Job well done, sir. Job well done. And I love the fact that you did it like show and tell. You actually had stuff to be able to.
Yeah. We're in our office here, and so one thing that any service companies out there, We love lunch and learns. We are eager to learn. So if you have something new that we may have, Delta Tech came by. They said, we have this system that allows you to cement so you can float your casing and circulate. You can also float your casing and cement, which is kind of cool because it's, torque is one of the biggest limiters there. So people come by and, we're eager to learn, and they also bring all sorts of stuff to show. So our office is cool. We got a lot of stuff to
got a
to play
collection
with.
of all kinds of stuff there.
That's right. The only thing that's missing is a 3D printed bed.
Oh, my office is not missing any of those. We have got plenty, absolutely plenty. So maybe I can drop by the K&M office someday.
Absolutely, would love to have you.
I think we've even been printing up some green ones.
Yeah.
They're a little bit brighter green than y'all's, so we'd have to.
If you print one, I want it. We'll call it David Gibson glasses orange. That's the color.
I do have a bright orange filament. Mr. Brad Watson says, "Great presentation. Thank you."
Thank you.
So, all right, guys. If y'all do have any questions, now's the time to be able to get them fired up, and we will start rolling through these as quick as we can. This question actually got answered in the comment section, but I'll let you. Can you please explain the pull down system again? Actually, it's right there.
I wish Christopher Cutts worked up in Canada. I don't have any experience with them. I just know that they're very common in Canada. It's a pulley system that pulls everything to the rig floor, and it's very common in Canada. Hey Jason.
Yeah,
give me 1 second. While I'm in the office, is Chris here?
Yeah.
Tell him to come here. All right, move on to the next question, and then I'll
okay.
And then we'll have him explain how this pull down system actually works.
Ken asks, please explain how hanging drill collars with a packer helps.
Yeah, I mean, so if you have, I'm talking about like an RTTS or a retrievable packer. With a retrievable packer, so if you think to the casing flotation. Remember the casing flotation, I have air-filled casing at the bottom that's light, and then in the vertical section, I have mud-filled casing that's heavy, right? And that overcomes the drag in the lower part. Well, so that you understand how that works, hopefully. Now, if I have a full mud system, then I have heavier casing here and heavier casing here. But what I want to do is I want to increase my weight in the vertical section so I can overcome that drag in the lower section. So if I would install it right in the vertical section, and the 10 collars or whatever, the 6 3/4 collars that I showed, with the packer is going to increase the weight by some 75,000 pounds or whatever the number was. Let me see if I can. I'll give you an actual number from right here. So from here, which is right around, we'll call it 45,000 to call it 120,000. Yeah, so it's like, call it 70,000 pounds. It's like getting a 70,000 pound roughneck to grab onto your casing and jump up and down and add weight to it and push it in the hole. And that guy would have cholesterol problems and heart problems.
He wouldn't be a roughneck. He would be in a completely different profession.
So I got Chris, come on over here. So you can't see, so just look at that camera right there. So this is Chris Cutts. He's the general manager at K&M. He's my in-house Canadian. So there was a question on how do the pull down systems work, because I talked about that, about pushing pipe in the hole. So I figured, you being Canadian, you must know something about it, because that's the only place that I know that uses them on a regular basis.
Yeah, so so in SAGD in Western Canada, because it's so shallow, they don't have much of a buckling issue, but they have more of a negative weight issue where they just physically can't force the pipe into the hole. So the rig pull down systems are a hydraulic system that's essentially anchored to the substructure. And then as they're picking up the casing with a pipe arm, they'll make it up to the next joint that's in the rotary table. And then this system will essentially grapple onto the pipe and just pull it into the ground, putting that weight against the substructure. Now, in some cases, these wells, they only go as far as they can go, because sometimes they can get to a point where they can physically be like lifting the rig off of the ground, because that's as far, that's the capability of the weight of the rig and how it can grip the pipe and actually force it into the ground using the hydraulic rams.
Nobody, in that case, what you can do is get a couple of super sacks of cow carb or whatever, yeah, put them on the rig floor just to add a little bit more weight. But
everybody at the rig site standing on the rig floor, so that you
get everybody from the camp and get everybody from the camp. But yeah, so sorry to pull you in.
There's
glad to contribute. Glad to be.
So in directional drilling, there's reactive torque, and with this, there's reactive pushing, I guess.
Yeah, that's right. I mean, it's so in both cases, like the drill collars, you're adding weight. With the pull down system, you're actually pulling the casing to the ground. But if that amount of so what he was saying is some of the pull capabilities of these systems are quite significant, to the point where it can actually lift the rig off the ground if the casing doesn't want to move anymore, if you have that much drag.
Golly. All right. That is some very interesting stuff that I never thought I mean, obviously I haven't been working in Western Canada enough. What are ways to reduce axial drag when running casing without adding weight to the surface?
Without adding weight to the surface? I'm not. This is one of the things that's problematic with virtuals, because I would like him to explain that a little bit more. But
I figure Eric's still watching, so he could probably jump back in there and explain that one. He's been on almost all of these, so we'll come back.
Depending on when he asked that might have been when I was talking about the drill collars or pushing. So the things that I talked about to reduce drag is you can change its direction. You ream your casing. You can reduce the weight of the casing by floating it. You can reduce your friction either by mechanical or some additives. Like when we talked about we said lubricants or beads. The guys that do the beads demo, they usually have like a jar of beads. They'll put it on your table, and then they'll put a book on top of it, and they'll give it a little push, and it'll shoot off the table, and they'll say, look at how low the friction is. When that happens, I would encourage you to take that jar of beads and just put it on the carpet. Just put a little bit on the carpet, put your book on the beads on the floor, and then give it a push and see if your book shoots across the floor. It's not going to have. So the point, like what I'm trying to mention is the beads will work in certain situations, like inside casing. If the casing is very clean, sure, the beads could have some effect. But if you have like a softer formation, or if you have a lot of cuttings where those beads are going to get embedded in the cuttings, they're probably not going to be as effective. If you want, the point is try it on situations that doesn't require, anytime that you are relying on reducing your friction, try it on a well that doesn't require it. Make sure that it is repeatable, that it actually does reduce friction and is repeatable, regardless of what the product is.
All right. Well then, there we go. Next one from Wad. Through having a threshold to follow, the 2,000 pound limit for side force is a nice guideline to have. Wouldn't more rotations or slow ROP, high RPM, for example, and an 1,800 pound force be more detrimental to the casing?
So there is it used to be malware. I don't know who, if they still, I think Halliburton bought them now. It's Seaware. Seaware is the program where you can put in what you are doing for your entire operation, and it'll try to see what how much casing wear you're going to have. The interesting part about this is, like, when so this is not a casing wear problem. I'm just going to walk through a key seating issue that when people try to do the right things, but actually and making the situation much worse. It was a 90-degree dog leg in the reservoir, right? The 90-degree turn. It wasn't a 90-degree dog leg. A 90-degree turn in the reservoir in a long reach well. Previously, there was not a lot of reaming. They drilled a lot of these wells. There was not a lot of reaming at connections. They wanted to be quick. So they just go, like, if the connection took 2 or 3 minutes, the company man would be pissed. But then all of a sudden, they start having key seating issues. And you go back and you look at it, and it was, they'd hired a new company man, and it was, his background is you drill stand down, you ream the entire stand, then you drill again. And so he had done this. And if you go past that curve and then you drill a long horizontal section, well, now when you ream up, there's quite a bit of tension there. So they started to develop key seatings and key seating in that 90-degree curve. Now they have a key seating issue. They're thinking rotation is what's causing. Like, you can't have a key. Well, typically you don't have a key seating issue. You don't have a casing wear issue due to tripping. The person that asked the question, it is absolutely correct that you need rotation. High side forces just going up and down, that's usually not an issue. So they know that rotation is causing an issue. They know that they have a key seating issue, so they drop their RPM and they continue to ream, and they back ream with a low RPM. So if you go back and you do the modeling, when you drop your RPM, and they're saying that they start convincing themselves, well, the longer I'm in this formation, the worse the key seating issue. So I need to drop my RPM, and I need to get out of the hole fast to solve this key seating issue. When you put both of those things in the program, your side forces absolutely skyrocket because you're tripping out. Your tension goes way up, and you're not converting that to torsional drag. You're keeping it, most of it, as axial drag. So your hook load is high. So even though you're going from 80 to 60 RPM, you're actually making the situation much worse. So this is a long way of going about answering the question. But I would be more concerned about, keeping it less than 2,000 pounds rather than the RPM itself. And if you lower your RPM, typically what you'll see is that your side forces go up, especially if you're back reaming. If you're back reaming and you drop your RPM, your side forces will go up if your trip speed stays constant. And then again, so this 2,000 pounds is just a guideline. I can throw out some things that I have learned along the way. It's very formation dependent. There's the Cook Inlet up in Alaska, very abrasive sand. They were going through drill pipe, through BHAs. They saw nowhere near and in areas where they had nowhere near 2,000 pounds of side forces. So that a very abrasive formation can drop this significantly. The other thing is the type of metal. So I worked with one operator that had steel casing, and then the bottom of their casing below where they planned to set the production packer was chrome. At the very bottom at your target entry, there's typically very low side forces there, but because it was chrome, they were eating away at the chrome casing. So they did that for corrosion purposes, but they were eating away the casing so much that they just said, well, it doesn't make any sense to try and save the casing for corrosion purposes if we're going to eat it away while we're drilling anyway. So they just dropped the casing, the chrome casing, and just ran steel casing all the way down, because of the casing wear issues that they're having with the chrome.
There you go. All right. Pull that one off. So after floating the casing to TD and starting the cementing operation, breaking the disc, where does the air go?
It's a good question. So I did explain that some people have circulated it out the long way. That's not something that what we would recommend. What we recommend is you install a cement head with no plugs in it on the top of your casing, and use that to burst the casing. And then on the cement head, you have two flow lines. The bottom line, you can use that to fill the casing. The top line, you can route that to your gas buster. Because as soon as when you rupture that disc, if you're standing on the rig floor when that happens, one, the casing will jump a little bit, so be prepared for that. Don't freak out. And then the other thing is you'll hear the air, the casing go on a vacuum, because all of that fluid column is going to drop. And then the next thing is you get all this air bubbling out. So air bubbling out, so typically what we do is you pressure up, you rupture that disc, you just let everything come to an equilibrium, and then you fill, half of your casing. What we used to do is we used to fill the casing while venting and try to find like the perfect rate to fill the casing before it starts coming out the top outlet. What we found to be the fastest way to do it is just close the top outlet, fill half of the casing, open and vent, fill it up 3/4 of the way, the casing 3/4 of the way, open and vent, and then just top off the casing. You can hear, like when you're at the rig and you open that top valve, you'll know when it stopped venting, because you can hear the air whistling across there.
There we go. Pull that one off. Another question here from Eric. Can't the normal force be high in lateral if there is buckling, particularly slide drilling?
So yes, absolutely. But like I said, I'm not too concerned about normal force while buckling, because that's just one occurrence. It's different than one. You really don't want to rotate buckled pipe. Rotating buckled pipe. So if you were to apply enough weight on bit while you're rotating to buckle the pipe, you'd get very erratic torque. You'd get high normal forces. Bending stresses can be high. A lot of bad things can happen by rotating buckled pipe. But sliding, we buckle pipe all the time while we're sliding. And it's not an issue because it's just a one-time occurrence. Like even the bending stresses associated with buckling the pipe when you're sliding, that's one fatigue cycle on the pipe. If you're rotating at just 20 RPM, that would be the equivalent of 20 slides where you buckled the pipe in 1 minute.
All right. Sorry, I forgot to pull off that one. This is a very general question here. Has anyone had experience with running a casing swivel?
If anybody's answered that, and I'd like to hear the answer to that also, because it's been presented to us and we know that it's out there. I just don't know anybody that's actually ran it.
There we go. So yeah, if anybody in the comment section wants to jump in there and let us know. So pull that one off. Zaid says, stiff string model is always the best model to consider for all casings, question mark?
No. I mean, it's our model is a soft string model. The way that we account for it, I would say over 95, 99%. Like we've worked on world record wells, but and we've been doing this for 40 years. I would say what's more important is accurate modeling, like accurate inputs, and an accurate a buckling prediction. When I say that, so there's I can tell you how our software differs from some other ones. The buckling resistance is driven by the base pipe that you run. So if you run screens, we put in the dimensions of the base pipe of the screens. If we put centralizers on pipe, it does not change the buckling resistance. Buckling resistance is not affected by rotation or sliding. There's some programs where when you rotate, it matches our prediction fairly accurately. While sliding, it'll say that the buckling resistance is like 3 times the amount of the buckling resistance while sliding, which we think is nonsense. And we're confident with our solution because we have 30, 40 years of field data to justify it.
All right. Alejandro says, thanks for the presentation. Is there a way to rotate the casing while cementing when you are above your torque limit? Any tool, procedure?
No, not if you're above your torque limit. You're not going to be able to rotate it. So some things
they're having this problem.
Yeah. I mean, if you run free floating centralizers, so like I did talk about fixed centralizers that you need those to be able to rotate your casing down. If you can get your casing down conventionally, then the free floating centralizers will actually result in lower torque during the cement job, because again, you always have to think of what's in contact with what and what's moving. So if you have free floating centralizers, the pipe is moving inside the centralizer. So using Western wall tool. So instead of this being a sleeve, just think of this as the centralizer. If this is the centralizer and your pipe is moving inside of it, now it's the size of your pipe. That's the effective radius. And if this was fixed to it and rotating with it, then it's the centralizer radius that is the effective radius. I will add also, if you're running a liner, you could have hydro connection, run a liner. I've seen liners with like 8 round, running tools, where it's like you've put the Ferrari of all connections on the casing, and then the point that's going to see the highest torque is actually the weak point. So if you have a liner, it needs to be the liner, your liner hanger, your running tool, all of that needs to be capable of the torque that you're going to see. I mean, the only other thing is to see if reach out to Delta Tech and see if the floated liner or floated casing. I mean, it would be a long operation, because to do that you need an inner string to be able to circulate and cement while the rest of the liner. Because typically, if you're floating your liner in, once you get down to bottom, you fill it up, and that's going to increase your torque. But the Delta Tech solution allows you to keep it floated and circulate. So I've mentioned them a couple of times. I don't want to think anybody's like, I'm not getting any kickback or anything. I just thought it was cool. I just thought it was a cool solution. So that's why I've mentioned them a couple of times.
All right. Alfredo says, great presentation, Mitch and Dave. What are your thoughts / experience with titanium drill pipe?
I have none. Because I know it's expensive. So I don't have any experience with titanium drill pipe. Not me personally, but inside the K&M office, one of our engineers has had a lot of experience with aluminum drill pipe because of how light it is. But yeah, sorry, can't help you with the titanium drill pipe.
All right. Is the recommendation to not rotate buckled pipe, does it apply to sinusoidal buckling as well, or just helical buckled pipe?
Helical, really. That's the one that you should be worried about. And the problem with rotating buckled pipe is it. I can't stress enough how important torque and drag modeling is, and how important correctly determining the onset of buckling is to making your job easier or harder. Because rotating buckled pipe is the onset of it is very similar to bit generated stick slip. Because if you have low weight on bit, you don't have any buckling, you probably don't have any bit generated stick slip, assuming you don't have any bit generated stick slip. And then if you start increasing your weight, and all of a sudden you start getting erratic torque, it's very easy to say, "Oh, this is generated from the bit now, because under lower weight on bit I was fine, but now I'm taking too big of a bite." When in reality, it might be that you're exceeding your buckling limit of your drill string, because there's no such thing as lockup when you rotate buckled pipe. What how it manifests itself, what you see at surface, is the side forces go up. It's like setting slips downhole, but then the slips are releasing slip and setting again. So it looks very close to highly erratic torque, very similar to stick slip, but it's just caused by rotating the helically buckled pipe.
All right. Last one here. On the buckling resistance while rotating, maybe it is because of twist.
Yeah, there's there have been SPE papers where they've actually gone into flow loops and put pipe into compression and then turn it and put it in compression, and they found that it buckled on the same. Western Wall Tools actually had a really interesting paper where they looked at because the same thing, like, so, and like when I'm confident in our software, I like our software. I mean, it's I'm going to be skewed towards it, but I try to give people solutions to use during whatever software you use. I don't care. I think our software is efficient and it'll make your job easier. But whatever you use or have to, sometimes organizations have to use certain type of software. I would say always do not model it with centralization. And so don't put centralizers on there. Don't put any, just leave the dimensions of the base pipe. Like if you had screens, what you do is you go in and change the adjusted weight to account for all the additional weight of the screens, and always model it with rotation. Because the software that I know of where it's vastly different between sliding and rotating, and it's the sliding that we don't agree with. So put like 5 RPM in there and model it that way.
Well, that brings us to the end of all the questions. I will say we've got a couple of people. Rawat says, thanks. Soren says, fantastic presentation, great initiative. Keep them coming. Thanks. David says, great presentation. Thanks. Masan, thanks for the presentation. It was great. Ian Purse, thanks, Mitch and David. Another great show. Fantastic presentation. Great presentation. So, yes, thank you all for taking the time to be able to watch and be here. Mitch, thank you so much for your presentation. Huge shout out and thanks to WWT for being the sponsor for today's show. Speaking of which, don't have my notes right here. right here
I
in
got
front
a
of me.
suggestion. I'm going to throw this
Okay.
out on the fly so it's documented. We're doing like 7 weeks or 8 weeks or whatever the number is of torque and drag. We're not talking about hydraulics at all. I think that should be our next mini series because there's there's so many things that you can talk about hydraulics also. I think we should cover that.
All right. I mean, and even Chris Cutt says, "Great work, Mitch." Herbert Carrington says, "Thank you."
Great work to Chris also to come in here and bail me out.
Yeah. So next week we've got Debbie who's going to be covering operations and real-time torque and drag. We'll be talking about drilling and surveying practices, high angle hole cleaning systems approach, wellbore stability and loss circulation, tripping practices, real-time monitoring considerations, and then finally on February 28th, we will have Brandon Foster back again to be able to wrap everything up. This week there is no Vidor Locksmith show. I'm taking the week off. We had somebody cancel on Friday, so I said I'm going to Cloudcroft to go enjoy the weekend. Long weekend for me. So I think that's it. Mitch, once again, thank you so much, WWT. Thank you guys so much. Anything else you'd like to leave the audience with?
Nothing at all. Just if you have any issues, to reach out to me. I guess I'll add my email address here at the bottom, and reach out to me if you got any questions, and I'll be happy to help you out.
There we go. There's Mitch's email. Feel free to spam him all you want. I mean, email him and ask questions. Well, Mitch, thank you so much. WTBT, once again, thank you guys for sponsoring the show. You guys be sure to tune in next Tuesday, the following Tuesday, and then here pretty quick, maybe we'll be doing a hydraulics mini series and maybe even get somebody from Kingdom to be able to come on and present on that one as well. That's all I've got. Thank you guys all so much. We will be dropping the presentation in a couple of days on LinkedIn, so stay tuned to look for that. We've got all of the old and previous episodes on LinkedIn and on YouTube if you want to go back and watch any of them. And let me find the little button here. And that's it. Thank you guys so much. As always, know your industry.